Over deep time, Earth's climate has followed a strange rhythm. Ice sheets grow and melt in a pattern that repeats roughly every 41,000 years, linked to a slow change in the tilt of Earth's axis. This subtle shift in sunlight across the planet has been powerful enough to reshape oceans, carve continents with ice, and rewrite the history of life again and again. Today we explore how this 41,000-year cycle works and why it matters. If you enjoy calm journeys into Earth's deep past, please like, subscribe and share, and tell us in the comments what puzzles you most about the Ice Ages and their hidden clockwork. Thank you for watching. Now let's begin. Earth moves around the Sun within a larger structure that includes the Sun, the planets, their moons, and smaller bodies all bound together by gravity. In this setting, Earth follows a path that is close to a single plane, and this path repeats with a period of about 1 year. The plane of Earth's orbit is often called the ecliptic, and it lies only slightly tilted with respect to the plane that best represents the average orbital motion of all the major planets, which is sometimes called the invariable plane of the solar system. The geometry of Earth's motion can be described precisely using a small number of parameters that specify the size, shape, and orientation of the orbit, and the orientation of Earth itself as it spins. These parameters are not fixed. They change slowly under the influence of gravity from the other planets and from the distribution of mass within the solar system. Because the changes are gradual and governed by well-understood physics, they can be calculated over many hundreds of thousands of years and even over several million years with useful accuracy. The regularity of these slow variations provides a natural set of cycles that operate on timescales similar to those inferred for the waxing and waning of large ice sheets. In the simplest description, the orbit of Earth is an ellipse with the Sun located close to one of the ellipse's focal regions. The average distance between Earth and the Sun stays close to a characteristic value that does not change much over the timescales relevant for glacial cycles. What does change measurably is the eccentricity of the orbit, which describes how elongated the ellipse is compared to a perfect circle, the inclination of the orbit relative to a reference plane, and the orientation of that ellipse in space. When eccentricity is small, Earth's distance from the Sun varies only slightly over a year. When eccentricity is larger, the difference between the closest and farthest points along the orbit becomes greater, and the timing of these points within the calendar year depends on how the ellipse is oriented relative to a fixed direction in space. Eccentricity is one element of a set of long-period cycles known as Milankovitch cycles. These cycles arise because the gravitational pull from other planets, especially Jupiter and Saturn, slowly modifies the parameters of Earth's orbit and spin. Over tens of thousands to hundreds of thousands of years, the combined effect of these interactions produces variations in eccentricity, changes in the angle of Earth's tilt, and a slow rotation of the axis in space known as precession. Taken together, these variations alter how sunlight is distributed over the surface of Earth as a function of latitude and season, even when the total amount of energy received from the Sun, averaged over a full year, remains nearly constant. The orientation of Earth as it spins can be described by two main quantities: the tilt of the axis relative to the orbital plane, and the direction in space toward which that axis points. The tilt, often called obliquity, is the angle between Earth's spin axis and a line that is perpendicular to the plane of the orbit. At present, this angle is a little more than 23 degrees, but it does not stay fixed. Over a characteristic period of roughly 41,000 years, the tilt oscillates between slightly smaller and slightly larger values. The direction in which the axis points also changes. As Earth spins, the axis traces out a slow conical motion in space, under the influence of gravitational torques from the Sun, and the Moon acting on the slightly flattened shape of the planet. This motion is called axial precession. The combined effect of axial precession and the precession of the orbital ellipse in space is sometimes referred to as precession of the equinoxes. It changes the timing of the seasons relative to Earth's position along its orbit, and therefore relative to the points of closest and farthest approach to the Sun. Each of these parameters follows a cycle with a characteristic timescale. Eccentricity varies with dominant periods of around 100,000 years and several 100,000 years. Obliquity varies with a main period of about 41,000 years. Precession-related cycles have characteristic periods of around 20,000 years and somewhat longer. These timescales are not arbitrary. They emerge from calculations of how Earth responds to gravitational perturbations in a many-body system. Numerical integrations of planetary motions and analytical treatments of celestial mechanics both show that the orbital elements of Earth exhibit quasi-periodic behavior over time, with these characteristic frequencies standing out in spectral analyses. The small departures from perfect periodicity arise because the solar system is a many-body gravitational system in which orbits interact and exchange angular momentum, but the main cycles remain stable over long intervals. The combined result is a pattern of slow, predictable modulation of the seasonal and geographical distribution of incoming solar radiation. The concept of Milankovitch cycles links these orbital variations to long-term climate variations by focusing on the way in which changes in eccentricity, tilt, and precession modify insolation at different latitudes and seasons. In the present section, the emphasis remains on the geometric and dynamical description of the cycles themselves. The key point is that Earth's orbit and spin are not fixed in time, but instead vary in a regular calculable way that naturally introduces cycles on timescales of tens of thousands to hundreds of thousands of years, setting a background rhythm within which other components of the Earth system may respond. Astronomers describe these cycles using sets of orbital elements defined at a chosen reference time, and then propagated forward and backward using equations of motion that include the gravitational influence of the major bodies. The reliability of such calculations is checked by comparing model predictions with precise measurements of planetary positions, lunar laser ranging, and the observed drift of the equinoxes over historical timescales. For intervals of a few million years, independent methods converge on a consistent picture of how Earth's orbital elements evolve, including the timing and amplitude of the main eccentricity, obliquity, and precession cycles. This agreement provides confidence that the long-period variations in Earth's motion can be treated as a known external forcing when studying slower components of the Earth system. Earth's axial tilt is a key parameter that links the geometry of its spin to the geometry of its orbit. The tilt can be described as the angle between Earth's spin axis and a line drawn perpendicular to the plane of its orbit. This angle is called obliquity. At present, obliquity is a little more than 23 degrees, but over long timescales it does not remain fixed. Instead, it oscillates within a limited range as gravitational forces from the Sun, the Moon and the planets act on Earth's slightly flattened shape. Because Earth spins, it is not a perfect sphere. It is slightly wider at the equator than at the poles. This equatorial bulge is a region on which external gravitational fields exert differential forces. The Sun and the Moon pull on this bulge and generate torques that try to reorient the spin axis. The balance between Earth's spin, which maintains the orientation of the axis, and these torques, which tend to tilt and precess it, produces a slow motion of the axis in space combined with gradual changes in the tilt angle. The resulting evolution of obliquity is not random. It follows patterns that can be understood using the equations of rotational dynamics and celestial mechanics. The axial tilt responds to a combination of influences including the strength and direction of the torques, and the rate at which Earth's orbital plane itself slowly shifts under the gravitational influence of other planets. When the natural precession rate of the spin axis approaches certain values that are related to the precession of the orbital plane resonances can occur and modify the amplitude and timing of obliquity variations. Detailed calculations that integrate Earth's rotational and orbital motion forward and backward in time show that the tilt angle oscillates with a dominant period of about 41,000 years, accompanied by smaller contributions at nearby periods. During these oscillations, obliquity varies between a little more than 22 degrees and a little less than 25 degrees. The exact limits and timing change slowly over millions of years, but over the time interval relevant for quaternary glaciations, the pattern is well described as a quasi-periodic cycle centered near 41,000 years. The presence of the Moon has an important role in this behavior. Because the Moon is relatively massive and orbits close to Earth, it contributes significantly to the torque on Earth's equatorial bulge, and therefore to the precession of the spin axis. This contribution helps to keep the axial tilt within a moderate range. Calculations that remove the Moon from the system show that Earth's obliquity would likely experience much larger and more irregular swings over tens of millions of years, while the actual Earth with its Moon follows a more stable path. This stability means that the obliquity signal can be treated as a relatively regular function of time, with a well-defined main period over the last few million years. The mathematical description of obliquity evolution often uses series of sines and cosines with specific frequencies and amplitudes derived from the underlying gravitational problem. When these series are evaluated over time, the obliquity signal appears as a near sinusoidal wave, whose maxima and minima correspond to times of higher and lower tilt. The phase of this wave, meaning the timing of its maxima and minima, can be traced over millions of years, giving an astronomically based timescale. Independent computational approaches, including direct numerical integration of the equations of motion, and semi-analytical solutions that decompose the problem into normal modes, agree on the main features of this obliquity history. In this way, the evolution of Earth's axial tilt is not just a conceptual idea, but a quantitatively constrained function of time. The physical meaning of changing obliquity is straightforward at the geometric level. The tilt determines which latitudes lean toward the Sun at different points in the annual orbit, and how high the Sun appears in the sky at a given latitude during different times of the year. Larger tilt angles increase the range of solar declination over the year, allowing the subsolar point to migrate farther toward each pole. Smaller tilt angles confine this migration to a narrower band around the equator. In a hypothetical case with zero tilt, there would be no seasonal cycle of solar elevation, whereas in a hypothetical case of very large tilt, the polar regions would alternately point almost directly toward and away from the Sun. Earth occupies an intermediate range, and its obliquity variations cause modest but significant adjustments to the geometry of sunlight over latitude and season. In the context of Milankovitch theory, the 41,000-year obliquity cycle is therefore identified as a major component of the external forcing that arises purely from orbital and rotational mechanics. Orbital eccentricity and precession provide the remaining major components of the slowly varying astronomical forcing that characterizes Earth's motion through space. Eccentricity describes how much the orbital path deviates from a perfect circle. When eccentricity is small, the orbit is nearly circular, and Earth maintains an almost constant distance from the Sun throughout the year. When eccentricity is larger, the orbit is more elongated so that Earth spends part of the year noticeably closer to the Sun and part of the year farther away. Mathematically, eccentricity is a dimensionless parameter between 0 and 1 that appears in the equations describing the shape of an ellipse, but in the context of long-term climate studies it is treated as a time-dependent function derived from astronomical calculations. For Earth, eccentricity remains modest, always far from extreme values, yet it varies enough over tens of thousands to hundreds of thousands of years to modify the seasonal contrast in solar radiation when combined with changes in precession. The evolution of eccentricity is controlled mainly by the gravitational perturbations from other planets, especially Jupiter and Saturn. As these massive bodies follow their own slowly precessing orbits, they exchange angular momentum with Earth's orbit and induce gradual shifts in its shape and orientation. The problem is well suited to analysis using secular perturbation theory, in which the short period variations associated with the one-year orbital motion are averaged out, leaving only the slow trends. Solutions of this problem show that Earth's eccentricity can be approximated as a sum of periodic terms with characteristic periods near 100,000 years and several 100,000 years. The resulting time series is not a pure single cycle, but a combination of modes whose interference produces envelopes of higher and lower eccentricity over million-year intervals. Despite this complexity, the amplitude of eccentricity variations and the timing of their main peaks and troughs over the past few million years are well constrained by modern astronomical solutions that integrate the equations of motion of the solar system with high precision. Precession in the orbital sense refers to the gradual rotation of the entire elliptical orbit within its plane. Even if the shape of the ellipse and the tilt of Earth's axis were fixed, the point of closest approach to the Sun, often called perihelion, would not remain aligned with a fixed direction in space. Instead, this point slowly shifts as gravitational perturbations alter the orientation of the orbit. This motion is called apsidal precession. At the same time as described earlier, Earth's spin axis precesses like a slowly turning top under the combined torques from the Sun and the Moon, acting on the equatorial bulge. The combination of axial precession and apsidal precession determines how the timing of the seasons relates to Earth's position along its orbit. If perihelion occurs near the time when the northern hemisphere is tilted toward the Sun, northern summers take place when Earth is relatively close to the Sun. If perihelion instead occurs when the northern hemisphere is tilted away, northern summers occur when Earth is relatively far from the Sun. Because axial precession proceeds in one direction, and apsidal precession proceeds at a different rate, the alignment between the seasons and the points of closest and farthest approach shifts over time. From the standpoint of climate forcing, this combined effect is often summarized as climatic precession. Climatic precession can be described by parameters that capture the product of eccentricity and the sine or cosine of the longitude of perihelion relative to the equinoxes. The relevant periods are on the order of 19 to 23,000 years, reflecting how long it takes for the seasonal calendar to move through a full cycle relative to the geometry of the elliptical orbit. The strength of climatic precession forcing depends on eccentricity, because if eccentricity is very small, the difference between closest and farthest approach is minimal even if the seasons align differently with the orbit. When eccentricity is larger, the same precessional shift produces a larger contrast in seasonal insulation between configurations in which a given hemisphere experiences summer near perihelion versus near aphelion. Astronomical solutions that track eccentricity, obliquity and precession simultaneously show that these parameters form a coupled system with distinct but interacting frequencies. Spectral analysis of computed orbital histories reveals peaks corresponding to the main eccentricity periods near 100,000 and 400,000 years, the obliquity period near 41,000 years, and the precession-related periods near 20,000 years. The phases and amplitudes of these components can be expressed as analytic series or as numerically tabulated functions of time. Because the underlying physics is gravitational and conservative on these timescales, these cycles are stable enough that their structure can be extended over millions of years with quantified uncertainties. In practice, teams that compute long-term orbital solutions use numerical integrators that solve Newton's equations for all major solar system bodies, while accounting for relativistic corrections, tidal effects, and the oblateness of the planets where relevant. The resulting trajectories are sampled at regular intervals to construct time series of orbital elements for Earth, including eccentricity inclination and the longitude of perihelion. Independent calculations that start from slightly different initial conditions and that use different numerical schemes converge on nearly identical histories over the past several million years. This agreement provides a measure of confidence that for the quaternary interval of interest, the evolution of eccentricity and precession is known with sufficient accuracy to serve as a fixed astronomical reference. In that role, the eccentricity and precession components of Milankovitch forcing define a slowly varying geometrical framework within which the distribution of solar radiation over latitude and season can later be quantified. Although the annual mean amount of energy that Earth receives from the Sun depends primarily on the average distance, which changes only slightly, as eccentricity varies, the combination of eccentricity with precession alters the timing and intensity of seasonal peaks and minima in top of atmosphere insolation. For the purpose of orbital theory, these changes are fully described once the time-dependent eccentricity, obliquity, and precession parameters are specified, and no additional empirical tuning is required at the astronomical level. From the standpoint of incoming solar radiation or insolation, the key effect of Earth's orbital and rotational geometry is to determine how much sunlight reaches the top of the atmosphere at a given latitude and time of year. This quantity can be computed from first principles using the inverse square dependence of irradiance on distance from the Sun and the projection of the solar beam onto a horizontal surface. In practice, insolation at the top of the atmosphere is often expressed as an average over a specific time interval, such as a day or a season, because the instantaneous value changes continuously with the rotation of Earth. The astronomical parameters that enter these calculations are the mean distance between Earth and the Sun, the eccentricity of the orbit, the position of Earth along its orbit at a given time, the obliquity or tilt of the spin axis, and the time of day, expressed relative to the local meridian. Once these parameters are specified, the solar zenith angle at any latitude and time can be determined, and from it the instantaneous insolation can be obtained. For long-term studies, the focus is usually on daily mean or seasonal mean insolation, because the climate system does not respond directly to variations on the timescale of a single rotation. Daily mean insolation at the top of the atmosphere at a given latitude depends on three main factors. The first is the distance between Earth and the Sun on that particular day, which is controlled by orbital eccentricity and Earth's position along its elliptical path. The second is the solar declination angle, which indicates how far north or south of the equator the Sun is directly overhead at local noon, and which is controlled mainly by obliquity and the progression of the seasons. The third is the length of daylight at that latitude on that date, which is determined by the combination of declination and latitude itself. The daily mean insolation is obtained by integrating the instantaneous insolation over the daylight period and dividing by the length of the day. When this procedure is carried out using the time-dependent orbital elements derived from astronomical calculations, A quantitative description arises of how insolation patterns change over tens of thousands of years. At low latitudes near the equator, the seasonal cycle of daily mean insolation is relatively small because the sun remains fairly high in the sky throughout the year, and the length of day varies only modestly. At high latitudes, particularly near the polar circles, and beyond, the seasonal cycle is much more pronounced. There, the sun can remain above the horizon for 24 hours during parts of the year, and remain below the horizon for extended periods during other parts. The height of the sun at local noon changes strongly with the seasons. As a result, daily mean insolation at high latitudes varies from very small values during polar night to relatively large values during midsummer, even though the annual mean insolation is lower than at low latitudes. Changes in obliquity directly modify this contrast. When tilt is larger, the subsolar point migrates farther toward each pole over the course of the year. This increases the solar elevation and the length of summer days at high latitudes, while also deepening the darkness of winter. When tilt is smaller, the seasonal migration of the subsolar point is more confined, and high latitude summers receive less intense and shorter duration sunlight. In addition to this obliquity-driven modulation, eccentricity and precession together alter the timing of the seasons with respect to Earth's varying distance from the Sun. Because eccentricity is modest for Earth, the annual mean insolation averaged over the whole planet changes only slightly as eccentricity varies. However, the seasonal distribution of insolation can change in a way that depends on both hemisphere and time of year. When Earth's perihelion occurs during Northern Hemisphere summer, the northern high latitudes experience somewhat higher summer insolation than they would if perihelion occurred at another time. When perihelion occurs during Northern Hemisphere winter, northern summers happen near aphelion, when Earth is slightly farther from the Sun, and summer insolation at high northern latitudes is reduced relative to the opposite configuration. The opposite applies to the southern hemisphere. This precession-driven modulation of seasonal insolation is strongest when eccentricity is relatively large, and becomes weak when eccentricity is near its minimum. By combining the effects of obliquity, eccentricity and precession, one obtains a full description of how daily mean insolation at each latitude evolves over time. This description can be expressed as a function of latitude day of year, and time in the past or future often referred to as an insolation history. Insolation histories computed from astronomical solutions reveal that the largest long-term variations in summer insolation at high latitudes are associated with the obliquity cycle of roughly 41,000 years, while precession introduces higher frequency modulations on timescales of around 20,000 years, whose amplitude depends on eccentricity. The pattern is not uniform across latitudes. Near the equator, the influence of obliquity is weaker, and precession-related changes in the timing of maximum solar elevation become more important for the seasonal cycle. At mid and high latitudes, obliquity plays a larger role because tilt strongly impacts both the solar elevation and the length of the day in summer. These differences mean that the insolation forcing has a distinctive spatial structure, with certain latitudes showing stronger sensitivity to particular orbital cycles. Formal analyses often decompose the insolation field into contributions from each astronomical parameter, making it clear which frequencies dominate at each latitude and season. Over the range of a few million years, the computed insolation histories are robust to reasonable variations in the assumed astronomical solution, because the structure of the underlying orbital cycles is stable. This stability allows insolation variations to be treated as a known external input on timescales relevant to glacial and interglacial cycles, In this context, an important outcome of these calculations is the identification of a persistent 41,000-year modulation in high-latitude summer insolation that arises directly from the obliquity cycle, accompanied by precession-related variations whose amplitude is set by eccentricity. Earth's insolation field has especially strong seasonal contrasts at high latitudes, and these contrasts are controlled largely by axial tilt. At a fixed latitude, the seasonal cycle of top-of-atmosphere insolation is determined by how the solar declination varies and by the length of daylight on each day of the year. Both of these factors depend directly on obliquity. When tilt is greater, the sun reaches higher maximum elevations in summer and lower minimum elevations in winter at a given latitude away from the equator. The corresponding daily paths of the sun across the sky become longer in summer and shorter in winter. When tilt is smaller, the opposite occurs. The extremes of solar elevation are reduced, and the range of day length over the annual cycle narrows. These geometric changes translate into systematic differences in daily mean and seasonal mean insolation. For latitudes equatorward of the polar circle's summer days become brighter and longer, when obliquity is higher, while winter days become darker and shorter. Poleward of the polar circles, the impact is even more pronounced because periods of continuous daylight and continuous darkness are involved. A higher tilt extends the duration of continuous summer daylight and deepens the winter interval during which the sun does not rise. A lower tilt shortens these periods and moves conditions toward a regime with less extreme seasonal asymmetry. The result is that changes in obliquity modulate not only the peak summer insolation, but also the integrated energy received over the warm season at high latitudes. Calculations of daily mean insolation as a function of latitude and day of year show that the sensitivity to obliquity increases with latitude. At low latitudes, a change of 1 degree in tilt produces only a small change in annual cycle amplitude. At high northern latitudes, the same change in tilt produces a much larger absolute change in summer season insolation. This occurs because high latitude insolation is dominated by the combination of a low solar elevation angle and large variations in day length, both of which respond strongly to tilt. When obliquity increases, high latitude summer days both lengthen and experience a higher maximum solar elevation, amplifying the change in total daily received energy. When obliquity decreases, both factors move in the opposite direction, reducing summer insolation. The dependence is such that the high latitude insolation response to obliquity forms a broad maximum in sensitivity at latitudes where large ice sheets have existed during the Quaternary, particularly in the northern hemisphere. In addition to tilt precession and eccentricity, jointly modify the seasonal cycle by shifting the phase of the seasons relative to Earth's distance from the Sun. However, for high latitudes, the dominant long-period modulation of summer insolation over the past few million years arises from obliquity. Precession-related effects introduce higher frequency variations on timescales of around 20,000 years, and their amplitude depends on eccentricity. But the underlying envelope of high-latitude summer insolation is paced by the roughly 41,000-year tilt cycle. This can be demonstrated by isolating the contribution of obliquity in formal calculations of insolation history. When only obliquity is allowed to vary while eccentricity and precession are held fixed, the resulting high-latitude summer insolation curves still show a clear regular pattern with a period near 41,000 years. When precession is included, additional oscillations appear, but the obliquity signal remains the primary low-frequency component at these latitudes. A useful way to characterize the seasonal contrast at high latitudes is to consider the difference between peak summer insolation and minimum winter insolation, or alternatively to consider the integrated insolation over a defined warm season. In either approach, obliquity variations impose a strong modulation. Higher tilt increases the difference between summer and winter, while lower tilt reduces it. The integrated summer half-year insolation, at for example 65 degrees north, experiences pronounced fluctuations that are closely correlated with changes in tilt. Such metrics are important because although the annual mean insolation at a given latitude may change very little, the ability of snow and ice to persist or melt depends disproportionately on conditions during the warm season. From the astronomical perspective, this means that obliquity-driven changes in high-latitude summer insolation represent a natural candidate for pacing the advance and retreat of large ice sheets. The spatial structure of obliquity forcing is also relevant. At a given time, a higher tilt enhances summer insolation across a broad band of high latitudes in both hemispheres. However, the presence of large land masses in the northern hemisphere, particularly in the latitude range where insolation sensitivity is high, means that the same astronomical forcing has different potential climatic impacts in the two hemispheres. The geometry alone does not prescribe where ice sheets form, but it does specify where the seasonal energy input is most strongly modulated by tilt. Over long time scales, sequences of high and low obliquity states impose a repeating pattern in which high latitude summers alternately become more and less capable of removing winter snow and thinning existing ice. The astronomical calculations themselves stop at the level of insolation. They do not dictate the climate response. Nonetheless, the pattern they define is clear at high northern latitudes. The amplitude of the seasonal cycle in top-of-atmosphere insolation varies with a dominant period of about 41,000 years, and this variation is set largely by the evolution of Earth's axial tilt. Quantitative studies often summarize high-latitude insolation variations using time series of summer solstice or summer half-year insolation at fixed latitudes. When these series are subjected to spectral analysis, the dominant peak near 41,000 years reflects the obliquity cycle, with smaller contributions at precessional periods and very minor power at the main eccentricity periods. This result is robust across different astronomical solutions because it arises from basic geometric relationships. It shows that at the level of purely astronomical forcing, the largest and most regular long-term modulation of the seasonal energy input to the regions where large ice sheets have existed is tied directly to the slow oscillation of Earth's axial tilt, and that this modulation has persisted throughout the Quaternary interval, considered in studies of glacial and interglacial cycles. When insolation histories are computed using astronomical solutions for Earth's orbit, and spin, a clear and persistent rhythm, appears in high-latitude summer values that is closely associated with the evolution of axial tilt. To obtain these histories, one selects a diagnostic quantity such as daily mean insolation at a specific latitude on the day of the local summer solstice, or the mean insolation integrated over a defined summer season. Using the time-dependent orbital elements, the solar declination day length and Earth-Sun distance are calculated for each date, and from these the daily mean top-of-atmosphere insolation is derived. Repeating this calculation over many tens or hundreds of thousands of years, while updating the orbital parameters generates a time series that represents how the energy input to a chosen latitude during summer changes as obliquity precession and eccentricity evolve. For latitudes where large quaternary ice sheets have been present, such as around 65 degrees north, these time series show that summer solstice or summer half-year insolation varies substantially on timescales of tens of thousands of years. When the spectrum of this variation is analysed, the dominant peak occurs near a period of 41,000 years, matching the main period of obliquity. Secondary peaks appear at periods associated with precession near 20,000 years and somewhat longer, and much weaker power appears at periods linked to eccentricity. In the time domain, this means that high-latitude summer insolation traces out a quasi-regular sequence of maxima and minima with spacing close to 41,000 years, modulated by shorter period oscillations linked to precession and by slower amplitude envelopes associated with eccentricity. The amplitude of the obliquity-related component is not negligible. For example, calculations of daily mean summer solstice insolation at 65 degrees north indicate that between times of low tilt and times of high tilt, the difference in incoming energy can reach several tens of watts per square meter. When integrated over the summer season, this translates into a substantial change in total energy input. Because the annual mean insolation at that latitude changes very little, the effect is almost entirely a modulation of the seasonal cycle rather than a shift in the overall annual energy budget. The phase of the 41,000-year component is tied closely to the phase of the obliquity cycle. Times when the tilt angle reaches local maxima correspond to times when high-latitude summer insolation reaches local maxima in the obliquity component. When obliquity passes through minima, the high-latitude summer insolation component associated with tilt also reaches minima. Precession introduces additional oscillations on shorter timescales, so the full insolation curve is not a perfect sinusoid. Instead, it can be represented as the sum of a dominant 41,000-year wave and faster precession-related waves whose amplitude is controlled by eccentricity. When eccentricity is small, the precessional contribution to high-latitude summer insolation is reduced, and the insolation record is more strongly dominated by the obliquity component. When eccentricity is larger, precession contributes a more prominent set of higher frequency oscillations superimposed on the obliquity-paced envelope. Across latitudes, the strength of the 41,000-year signal varies. At low latitudes, the seasonal cycle of insolation is relatively small and depends less strongly on tilt. Their precession-related variations in the timing and symmetry of the seasonal cycle tend to contribute more to long-term insolation changes. At mid-latitudes, both obliquity and precession play visible roles. At high latitudes, particularly in the northern hemisphere where large land areas exist, the 41,000-year component linked to obliquity dominates the low-frequency part of the summer insolation spectrum. This latitudinal structure is a straightforward geometric consequence of how tilt affects the solar elevation and length of day, and of how eccentricity and precession redistribute insolation between seasons and hemispheres without greatly altering the global annual mean. Over intervals of a few million years, numerical orbital solutions provide continuous time series of obliquity precession and eccentricity. When these are used to compute high-latitude summer insolation, the resulting record displays a long sequence of obliquity-paced cycles. The detailed amplitude and phase of the cycles drift slowly because the underlying astronomical frequencies are not perfectly commensurate, and because long-period modulations in eccentricity and in the obliquity amplitude itself occur. Nonetheless, the presence of a recurring peak near 41,000 years in spectral analyses of insolation at high latitudes is consistent across different astronomical solutions and different methods of insolation calculation. Various definitions of a summer insolation metric, such as insolation at a fixed day of the year at the day of maximum solar elevation or averaged over a fixed warm season, all recover a strong 41,000-year component at latitudes where tilt has the largest influence on the seasonal cycle. This robustness reflects the fact that all such metrics are ultimately controlled by the same geometric factors, the path of the sun in the sky and the duration of daylight, both of which respond directly to changes in axial tilt. For studies that seek to relate orbital forcing to longer-term variations in other parts of the Earth system, it is therefore common to adopt high-latitude summer insolation time series as a compact representation of the astronomical forcing. These series encapsulate the combined effect of obliquity precession and eccentricity on the seasonal energy input at locations of interest, while retaining the dominant 41,000-year rhythm imposed by obliquity. Within the insolation framework itself, without yet invoking any climate response, the conclusion is that high northern latitudes experience a repeating modulation of summer energy input, with a main period of roughly 41,000 years superimposed on shorter precessional oscillations, whose strength depends on the varying eccentricity of Earth's orbit. This modulation is fully determined by the time evolution of Earth's orbital elements and spin orientation as given by astronomical calculations, and does not require additional empirical parameters to describe its structure over quaternary timescales. The atmosphere forms a thin continuous fluid shell around Earth, and it responds to changes in incoming solar radiation by adjusting its temperature density and circulation patterns over a wide range of timescales. Climate defined as the statistics of atmospheric conditions over decades and longer reflects a balance between the energy Earth receives from the Sun and the energy it emits back to space. Orbital variations do not strongly alter the global annual mean of incoming energy, but they do change its distribution with latitude and season. When insolation at the top of the atmosphere shifts in this way, the atmospheric column at each latitude experiences small but persistent changes in net radiative forcing. Over many seasons and years, these changes lead to adjustments in temperature gradients, pressure fields, and wind systems. The atmosphere interacts with both incoming solar radiation and outgoing long-wave radiation emitted by Earth's surface and by the atmosphere itself. Gases such as water vapor, carbon dioxide, and methane absorb and emit long-wave radiation, producing the greenhouse effect that maintains Earth's surface at temperatures compatible with liquid water. Clouds and aerosols scatter and absorb solar and terrestrial radiation, modifying the vertical and horizontal distribution of heating. When orbital forcing alters the seasonal and latitudinal pattern of insolation, the radiative heating profile changes correspondingly, even if the overall energy budget remains nearly unchanged. The resulting imbalances between radiative heating and cooling induce changes in temperature, which in turn affect density and pressure, leading to adjustments in large-scale circulation. At the planetary scale, the general circulation of the atmosphere is organized into broad cells. Near the equator, rising warm air and convection form the ascending branch of the Hadley circulation, which transports energy poleward in the upper troposphere and returns air toward the equator near the surface. At mid-latitudes, baroclinic eddies and jet streams form where strong horizontal temperature gradients exist, especially in winter. Near the poles, colder, denser air tends to sink and form relatively high surface pressure. The strength and position of these features depend on the equator to pole temperature contrast and on the seasonal cycle of heating. When orbital variations change high-latitude summer insolation, they effectively alter the seasonal heating at the boundaries of this circulation system. Over thousands of years, even modest changes in high-latitude summer insolation can influence the average temperature of the lower atmosphere in those regions by changing the cumulative energy input during the warm season. If summers become slightly warmer on average, the meridional temperature gradient between low and high latitudes may weaken during part of the year, which tends to modify the strength and position of mid-latitude jets and storm tracks. If summers become slightly cooler, the gradient may strengthen, potentially favouring different configurations of the jet streams and associated eddy activity. Such changes in the general circulation affect patterns of moisture, transport storm frequency, and regional precipitation, which together contribute to the long-term climate response to orbital forcing. The atmosphere also exhibits internal variability, arising from nonlinear interactions between winds, temperature gradients, and planetary rotation. On timescales shorter than a decade, this variability can be large compared with the direct effect of orbital forcing in any single year. However, on timescales of tens of thousands of years, the orbital signal acts as a slow boundary condition that biases the statistics of atmospheric states toward configurations that are more consistent with the altered insolation pattern. Climate models that include only an atmosphere and a simplified surface can reproduce this behavior when forced with orbital configurations that change obliquity and precession. They generate systematic shifts in seasonal temperature and precipitation fields that track the imposed insolation changes, even though year-to-year variability remains substantial. Over continents where the thermal inertia of the surface is relatively small, atmospheric temperatures can respond more rapidly to changes in seasonal insolation. Over oceans where heat capacity is much larger, the near-surface air temperature is constrained by the slower response of the upper ocean mixed layer. As a result, orbital scale changes in insolation tend to produce larger and more immediate responses in continental interior climates than over open ocean regions. This land-sea contrast influences pressure patterns and monsoon systems. In regions where seasonal heating of land relative to adjacent ocean drives, monsoon circulations such as parts of Africa and Asia, precession-driven changes in the timing and intensity of peak insolation can significantly affect the strength and spatial pattern of monsoon rainfall. When climatic precession aligns maximum insolation with the local summer over a large land mass, the resulting enhanced land surface heating can strengthen monsoon circulation and increase precipitation. When the alignment is different, the same regions may experience weaker monsoon systems. In this way, the atmosphere transmits aspects of the orbital forcing into distinct regional climate responses. The vertical structure of the atmosphere also adjusts. Radiative cooling to space and convective heat transport together maintain a characteristic lapse rate in the troposphere. When insolation changes alter surface temperatures, the vertical temperature profile shifts to maintain approximate radiative convective equilibrium. These adjustments affect cloud formation, water vapor distribution, and large-scale stability. Because water vapor is a strong greenhouse gas, changes in atmospheric moisture content constitute an important feedback. Warmer air can hold more moisture, which can enhance long-wave trapping and further modify the energy balance. Over orbital timescales, this feedback operates alongside the primary insolation, forcing to shape the magnitude and pattern of atmospheric temperature changes. In polar and subpolar regions where seasonal insolation changes are strongest, the atmosphere's response is closely tied to the surface energy balance. Changes in the frequency and intensity of cold air outbreaks, the position and strength of the polar vortex, and the behavior of storm tracks influence how efficiently heat and moisture are transported to and from high latitudes. These processes determine the conditions under which snow can accumulate and persist from one year to the next, and they influence the surface radiative budget by affecting cloudiness and near-surface humidity. Although the detailed evolution of snow-cover sea ice and ice sheets involves additional processes that extend beyond the atmosphere, the atmospheric circulation sets the pattern of temperature and precipitation that these slower components experience. From the perspective of orbital forcing, The atmosphere acts as an intermediate layer that translates changes in the distribution of solar radiation at the top of the atmosphere into spatially and seasonally structured changes in surface climate. The response is expressed through altered temperature gradients, modified pressure systems, and reorganized wind and precipitation patterns. Over timescales of many thousands of years, these adjustments produce a climate background against which other parts of the Earth system, including the hydrological cycle and frozen water stored at the surface, operate. The atmosphere does not store a large amount of heat compared with the ocean, but it controls the exchange of energy and moisture between space, the surface, and the deeper components of the climate system, and in this role it mediates the climatic imprint of the slowly varying obliquity precession and eccentricity cycles. The oceans cover most of Earth's surface and contain the majority of the climate system's movable heat content, so they play a central role in setting how climate responds to orbital forcing on timescales of thousands of years. Seawater has a much larger heat capacity than air or land, meaning that a given amount of energy input produces a smaller temperature change. As a result, the oceans act as a large thermal reservoir that can store and redistribute heat as the pattern of insolation changes with latitude and season. The upper ocean is organized into a mixed layer where wind-driven turbulence and waves continually stir the water, and a thermocline where temperature decreases more rapidly with depth, and vertical mixing is weaker. Below the thermocline lies the deep ocean, in which water masses are formed at high latitudes where surface water becomes dense enough to sink. Each of these layers responds to orbital forcing on different timescales. The mixed layer, typically tens of meters to a few hundred meters thick, can adjust within years to decades, while the thermocline and deep ocean respond on timescales of centuries to millennia. When high-latitude summer insolation increases due to changes in obliquity or precession, the immediate effect is felt at the surface as warmer air temperatures and modified wind patterns. These changes alter the net heat flux at the ocean surface through sensible heat exchange, latent heat associated with evaporation and long-wave and short-wave radiation. The mixed layer absorbs part of this additional energy and warms, but the rate and extent of warming depend on the efficiency of vertical mixing and lateral transport. In regions where winds drive strong upwelling surface waters that have been heated by increased insolation can be replaced by cooler, deeper water, which limits the surface temperature rise and transports heat downward. In downwelling regions, warmer surface water can be carried into the thermocline and deeper layers more directly. Through these processes, the ocean tends to smooth and delay the climate response to orbital scale changes in insolation. The large-scale circulation of the ocean consists of interacting wind-driven and density-driven components. In the upper ocean, winds generate currents that form gyres in each major basin, and that contribute to western boundary currents that carry warm water poleward along the western sides of ocean basins. These currents transport heat from low to higher latitudes and influence the climate of adjacent continents. The strength and position of wind-driven currents depend on wind stress patterns at the surface, which are themselves controlled by atmospheric circulation. When orbital forcing alters atmospheric temperature gradients and pressure fields, the associated changes in wind stress can modify surface currents and the distribution of sea surface temperature. Over longer intervals, these adjustments can reorganize where and how efficiently heat is transported within and between basins. The density-driven component, often called the overturning circulation, arises because seawater density depends on both temperature and salinity. At high latitudes, especially in the North Atlantic and around Antarctica, surface waters can become cold and salty enough to sink from the surface into the deep ocean. This sinking is balanced by upwelling elsewhere, forming a global scale loop that connects surface and deep waters. When high-latitude climates cool, sea ice can expand and surface waters can become denser through cooling and brine rejection during sea ice formation, potentially favouring deep water formation in some regions. When climates warm, the balance among cooling freshwater input and mixing changes, altering the rate and location of deep water formation. Because the deep ocean exchanges heat and dissolves substances with the surface, only slowly changes in the overturning circulation can store anomalies of temperature and salinity over many centuries. In the context of orbital forcing, this means that variations in high-latitude insolation and atmosphere conditions can be integrated by the ocean into slower, larger-scale changes in the thermal state of the climate system. The ocean also interacts with the climate system through its role in the global cycles of freshwater and sea ice. Surface salinity is affected by evaporation, precipitation, river runoff, and the melting and freezing of sea ice. Orbital scale shifts in atmospheric circulation, and precipitation patterns influence these terms in the freshwater budget. For example, when precession enhances summer insolation over a monsoon region, stronger monsoon rainfall can increase river discharge and freshwater input to nearby coastal seas, reducing salinity in the upper ocean. At high latitudes, changes in the seasonal extent of sea ice modify both the surface albedo and the insulation between the relatively warm ocean and the cold atmosphere. A more extensive sea ice cover reduces wintertime heat loss from the ocean to the atmosphere and reflects more solar radiation in spring and summer, while a reduced sea ice cover allows more ocean heat to be released in winter and more solar radiation to be absorbed in summer. These interactions affect the vertical stratification of the upper ocean and the stability of the water column, which in turn influence the ease with which surface waters can be mixed downward, or deeper, waters can reach the surface. Another important aspect of the ocean's role is its interaction with the global carbon cycle. Carbon dioxide dissolves in seawater where it participates in a series of chemical reactions involving carbonate and bicarbonate ions. The capacity of the ocean to store carbon depends on temperature, alkalinity, and circulation. Cooler waters can hold more dissolved carbon dioxide, and deep waters can accumulate carbon over long periods if exchange with the atmosphere is limited. Changes in surface temperature, ocean mixing, and the pattern of nutrient supply can influence the partitioning of carbon between the ocean and the atmosphere. On timescales of thousands of years, these processes can contribute to feedbacks that amplify or moderate the climatic impact of orbital forcing, although the exact quantitative contribution of ocean carbon uptake and release in past glacial cycles is constrained by multiple interacting mechanisms. In addition to heat and carbon, the ocean stores and redistributes other traces such as nutrients and oxygen, which affect marine ecosystems and biogeochemical reactions that themselves can modify greenhouse gas concentrations. The response of the ocean to orbital forcing is therefore multifaceted. It includes direct thermal adjustment of the surface and upper ocean, to changes in insulation, reorganization of wind-driven and density-driven circulations that transport heat, and salt modulation of sea ice and freshwater budgets that shape stratification and deep water formation, and longer-term changes in carbon storage that influence atmospheric composition. Compared with the atmosphere, the ocean's large heat capacity and slower circulation make it a key medium through which the climate system integrates and filters the astronomical forcing associated with obliquity, precession, and eccentricity. The combined effect is to distribute orbital-scale energy anomalies in space and time, influencing the background conditions under which snow sea ice and continental ice sheets can grow or shrink, even though the direct orbital forcing appears initially only as changes in insulation at the top of the atmosphere. Snow cover and sea ice form the fast-changing components of the cryosphere, and they respond sensitively to orbital scale changes in insolation through their influence on the surface energy balance. Both are characterized by a high reflectivity or albedo for visible solar radiation. Fresh, dry snow reflects most of the incident sunlight, while darker surfaces such as open ocean or bare ground absorb a much larger fraction. Sea ice also reflects more sunlight than open water, especially when it carries a layer of snow. This contrast means that changes in the area and duration of snow and sea ice covered directly affect how much of the incoming solar energy is absorbed at the surface versus returned to space. When climate cools and snow or sea ice expand, the planetary albedo increases, reducing the absorbed solar energy and reinforcing the initial cooling. When climate warms and these bright surfaces contract, albedo decreases, absorbed solar energy increases, and the warming is reinforced. This behavior constitutes a positive feedback in the climate system. The distribution of seasonal snow cover is governed by the balance between precipitation temperature and radiative and turbulent fluxes at the surface. Snow accumulates where precipitation falls as snow rather than rain, and where temperatures remain low enough to prevent rapid melt. In many mid and high latitude continental regions, snow cover develops in autumn, grows through winter, and then retreats in spring and early summer. The timing and duration of this cycle are sensitive to relatively small changes in seasonal mean temperature. A modest increase in spring or early summer temperature can shift the date at which snow begins to melt or the rate at which it disappears, altering the length of time that high albedo snow remains on the ground. Because snow-covered land reflects much more sunlight than snow-free land or vegetated surfaces, these timing shifts influence how much solar energy is absorbed during the critical part of the year when insolation is rising toward its maximum. At high northern latitudes where insolation sensitivity to obliquity is strong, the interaction between snow cover and seasonal energy input becomes particularly important. Sea ice forms when surface ocean temperatures fall to the freezing point and sufficient heat is lost to the atmosphere to allow ice growth. In the Arctic and around Antarctica, sea ice undergoes a pronounced seasonal cycle. The area of sea ice expands during the cold season and contracts during the warm season. The exact pattern depends on regional ocean circulation, atmospheric conditions, and coastline geometry. Sea ice changes the surface energy balance in several ways. In addition to its higher albedo compared with open water, it acts as an insulating layer that reduces the exchange of sensible and latent heat between the relatively warm ocean and the colder atmosphere, especially in winter. It also modifies the roughness felt by the wind, affecting momentum transfer and the generation of surface currents. When sea ice is covered by snow, its effective albedo increases, further enhancing the reflection of solar radiation during the sunlit months. As orbital forcing alters the seasonal distribution of insolation, particularly at high latitudes, the formation and melt of sea ice respond through adjustments in surface temperature and heat fluxes. If high-latitude summers become slightly warmer, on average sea ice extent during late spring and early summer tends to be reduced, exposing more open water at times when solar elevation is relatively high. Open water absorbs more solar energy than snow-covered ice, leading to additional warming of the surface ocean. This stored heat delays sea ice formation during the following autumn and early winter, extending the period of low albedo conditions and reinforcing the warming effect. Conversely, if summers become slightly cooler, sea ice can persist longer into the sunlit season, maintaining higher surface albedo and limiting ocean heat uptake, which favors earlier and more extensive sea ice formation in the following cold season. This sea ice albedo feedback operates on seasonal to multi-decadal timescales, yet when orbital forcing biases the seasonal insolation pattern, over many thousands of years its integrated effect contributes to the longer-term climate response. Snow and sea ice feedbacks interact with the atmosphere and ocean. Increased snow cover or sea ice extent cools the overlying air through reduced surface absorption of solar radiation and suppressed upward heat flux from the surface. Cooler air tends to be denser, which can influence the structure of surface pressure fields and the strength of temperature gradients, feeding back on wind patterns and storm tracks. Over the ocean, changes in sea ice formation and melt affect surface salinity and stratification, because freezing tends to reject salt into the underlying water, and melting adds fresh water. These changes influence density-driven circulation and mixed layer depth, which in turn affect how heat and freshwater anomalies are stored and redistributed. In this way, the relatively fast response of snow and sea ice to orbital scale insolation variations is linked to slower adjustments in ocean structure and circulation. The spatial distribution of snow and sea ice also matters. Snow that persists through the warm season on high plateaus or at high latitudes exerts a stronger radiative influence than snow that melts during early spring, because it continues to reflect strong solar radiation. Sea ice that covers regions of typically high summer insolation modifies the absorbed energy more significantly than ice, persisting where the sun remains low in the sky. The geometry of continents and ocean basins therefore shapes how snow and sea ice feedbacks project onto the orbital forcing pattern. For example, in the northern hemisphere, large land areas at latitudes where summer insolation is sensitive to obliquity provide wide regions where snow cover can modulate surface albedo over substantial areas, while in the southern hemisphere the predominance of ocean and the different distribution of land limits the extent of permanent or long-lasting snow cover outside Antarctica. Over longer timescales, changes in vegetation and soil properties can interact with snow feedbacks. If cooler climates favour more open, less forested landscapes in some regions, snow may be able to persist more effectively on the ground, because forest canopies can intercept snowfall and modify the surface radiative properties. Conversely, warmer climates that allow forests to expand into previously open snow-dominated regions can alter how snow accumulates and melts, affecting the net albedo effect. These land surface changes occur through ecological and geomorphological processes that respond to climate over centuries and longer, and they add an additional layer of complexity to how the snow albedo feedback operates in different regions. Despite this complexity, the basic mechanism remains the same. Snow and sea ice provide a bright reflective cover that, when present, reduces the absorption of solar radiation at the surface. Orbital scale changes in high latitude insolation modify the conditions under which these covers form and decay, leading to systematic variations in their spatial extent and duration. Through their impact on albedo insulation and surface exchanges of heat and freshwater snow and sea ice, feedback on atmospheric and oceanic conditions, amplifying or moderating the climatic effect of the underlying insolation variations. On timescales of tens of thousands of years, these feedbacks contribute to the translation of the astronomical forcing, especially the 41,000-year obliquity cycle, into changes in regional climates that are relevant for the persistence of frozen water at the surface. Continental ice sheets are large, thick bodies of ice that spread over wide regions of land and persist for many tens of thousands of years when climatic conditions allow net accumulation of snow to exceed melt. In the Quaternary period, Extensive ice sheets have covered much of northern North America and northern Eurasia, during glacial stages thickening to heights of several kilometers in their central regions and extending toward lower latitudes along their margins. Their formation begins with ordinary snowfall that does not fully melt during the warm season. When snow persists from one year to the next, it is buried by subsequent winters of accumulation. Under the weight of overlying layers, the snow crystals become compacted, air is expelled, and the material transforms through firn into glacial ice, with higher density and distinct mechanical properties. Once a sufficient thickness is reached, the ice begins to deform under its own weight and flow downslope, converting local snowfields into connected ice masses that can coalesce into regional ice sheets. The initiation and expansion of such ice sheets depend on the balance between processes that add mass, primarily snowfall and the refreezing of meltwater, and processes that remove mass including surface melt, sublimation calving at marine margins, and basal melt, where the ice is in contact with relatively warm bedrock or ocean water. Climate sets this balance through air temperature, precipitation, cloud cover, wind, and the radiative conditions at the surface. Orbital forcing influences these climatic variables by altering seasonal and geographical insolation patterns, with high latitude summer insolation playing a critical role. When summer insolation at high northern latitudes is reduced over many successive cycles of the seasonal cycle, summers are cooler on average, and snow that accumulates during winter is more likely to persist through the melt season. Under such conditions, the elevation at which annual mean accumulation becomes positive shifts to lower heights, and potentially to lower latitudes, allowing existing mountain glaciers and small ice caps to expand and fill adjacent basins and plateaus. As ice thickens, the surface of the growing ice sheet rises to higher elevations, where temperatures are lower and the atmosphere is thinner and typically drier. This elevation effect reduces surface melt and can favour further accumulation in the interior, even if conditions at lower elevations remain marginal. At the same time, the expanding ice sheet modifies the local and regional climate by changing surface albedo moisture sources and the pattern of atmospheric flow over and around its topography. A continuous ice cover reflects much more solar radiation than a mixture of snow, free land, and vegetation, leading to a reduction in absorbed solar energy over the ice sheet region and its immediate surroundings. This reduction cools the overlying air, reinforces low-level temperature inversions in winter, and shifts pressure patterns which can steer storm tracks and moisture transport. In some configurations, the presence of a large ice sheet can focus precipitation on its flanks, where moist air is forced to ascend over the ice, increasing snowfall in accumulation zones near the margins, while leaving the interior relatively dry. The net effect on growth depends on how these changes interact with the background orbital forcing. The mechanics of ice flow also influence how ice sheets develop their shape and extent. Glacier ice behaves on long timescales as a very viscous fluid that deforms under stress. The driving stress arises from the component of the ice's weight that acts parallel to the underlying slope. In the interior, where the ice is thick and gradients are small, flow is slow and dominated by internal deformation. Toward the margins, ice can thin, gradients can steepen, and the basal conditions can change. Where the bed is frozen, motion is limited and the ice moves slowly. Where the base is at the pressure melting point and water is present, sliding can occur, and ice can move more rapidly over soft sediments or bedrock. These processes determine how quickly ice added in the accumulation zones is transferred toward the margins, where it is eventually lost by melting or calving. Orbital scale changes in climate do not alter the basic physics of ice flow, but they change surface mass balance and basal conditions in ways that can accelerate or slow expansion. For example, cooler summers and extended snow cover favour thickening in advance. At the same time, colder conditions can reduce basal water supply, in some regions potentially limiting sliding. Warmer intervals increase surface melt, thin the margins, and can increase basal water, where meltwater reaches the bed, potentially changing flow regimes. The spatial pattern of land and ocean in the Northern Hemisphere affects where ice sheets can form and how far they can expand. Large continental interiors at latitudes where high latitude summer insolation is sensitive to obliquity provide broad areas where snow can accumulate and persist. When conditions are favourable, ice sheets can extend from these interiors toward continental shelves. Where bedrock topography dips below sea level inland of present coasts, ice can become grounded on submarine platforms, forming marine-based portions that are in contact with ocean water at their margins. Such sectors can be particularly sensitive to changes in sea level ocean temperature and basal melt, but the basic requirement for their existence remains a climate in which net accumulation persists over the relevant areas. Over many tens of thousands of years, sequences of orbital configurations that repeatedly produce low-high latitude summer insolation can allow ice sheets to grow in a stepwise manner. During intervals of particularly low summer insolation, accumulation may strongly exceed ablation and the ice sheet advances. During intervening intervals with somewhat higher summer insolation, but still below a threshold for large-scale retreat, the ice surface may readjust more slowly, with changes concentrated on the margins while the interior remains thick. This cumulative growth process is associated with the role of obliquity in modulating the ability of summer to remove winter snow, but the exact temporal evolution also reflects how snow cover sea ice atmosphere and ocean have already adjusted. Large ice sheets, once established, exert a strong control on their own local climate through the combined effects of surface albedo elevation and induced circulation patterns, making them relatively resistant to short-lived changes but responsive to sustained shifts in high-latitude summer insolation. Ice sheet models that couple simplified representations of mass balance with ice dynamics show that when forced with variations in high-latitude summer insolation, consistent with astronomical solutions, ice sheets can grow over several obliquity cycles under sustained periods of lower summer insolation. The exact timing and amplitude of growth depend on model parameterizations of snowfall melt and sliding, but across many such studies a common feature is that reduced high latitude summer insolation promotes the slow expansion and thickening of Northern Hemisphere ice sheets. In this way, the obliquity-paced modulation of summer insolation can act as an external control on the conditions that govern the advance of large ice sheets, while the internal physical processes of snow, transformation, ice flow and climate feedbacks determine the detailed path of their growth over orbital timescales. Over tens of thousands of years, the evolution of continental ice sheets can be described in terms of mass balance, which is the net result of all processes that add and remove ice. Mass balance can be defined locally at each point on the ice surface and integrated over the entire ice sheet to obtain the total change in ice volume. At the surface, accumulation consists mainly of snowfall and the refreezing of meltwater that percolates into the snow and firn layers. Ablation includes surface melt that runs off or evaporates sublimation directly from the ice or snow surface, and the mechanical loss of ice by calving where glaciers or ice streams reach the ocean or large lakes. Basal processes provide additional gains and losses. In some regions, freezing of water at the base of the ice sheet adds mass while melting. At the bed removes mass and can produce liquid water that affects sliding. The sign and magnitude of the local mass balance depend on air temperature, precipitation, radiation, wind, and the underlying topography and bed conditions. Climate determines the large-scale pattern of these controlling variables, and orbital forcing influences climate on long time scales by modulating seasonal and latitudinal insolation. When summer insolation at high northern latitudes is relatively low for many consecutive obliquity cycles, average summer air temperatures in those regions tend to be lower than they would otherwise be, other factors being equal. Under such conditions, the altitude at which annual surface mass balance becomes positive, often called the equilibrium line, can shift toward lower elevations and latitudes. Below this line, annual melt exceeds accumulation, and above it, accumulation exceeds melt. A lower equilibrium line favors the growth of ice on high plateaus and uplands, and supports the expansion of existing ice caps. As ice thickens, its surface rises to higher altitudes where air is colder, and summer melt is weaker, reinforcing positive mass balance in the interior. At the same time, the extent of the ablation zone near the margins where net melt occurs changes as the ice front advances or retreats. Over the full ice sheet, the total mass balance reflects the competition between expanding accumulation areas in the interior and the changing size and intensity of ablation areas along the margins. The time response of ice sheets to a changing climate is not instantaneous. Even when atmospheric and oceanic conditions shift toward a cooler state, with reduced high-latitude summer insolation, it takes many centuries to millennia for ice sheets to grow to a new equilibrium size. The adjustment timescale is controlled by the rate at which snow can be converted to ice and advected from the accumulation zones to the margins by the viscosity of ice, by the width of the ablation zone, and by the geometry of the underlying bed. Simple models that treat ice thickness as a diffusing field show that the characteristic timescale for large-scale thickness changes is on the order of tens of thousands of years for ice sheets of continental scale. This implies that the mass balance response to obliquity paced insolation forcing can be phase-lagged. Periods of low obliquity and low high-latitude summer insolation initiate conditions favorable for growth, but the maximum ice volume can occur several thousand years after the strongest forcing anomaly as the ice sheet gradually accumulates mass. Conversely, when obliquity increases and high-latitude summers become more intense, surface melt intensifies, the equilibrium line rises to higher elevations and ablation zones widen. The interior accumulation zones may still receive snowfall, but the net mass balance can become negative if enhanced melt and calving losses at the margins exceed the inland gains. The decay of ice sheets under such conditions can also span several millennia, during which the ice surface lowers, the margins retreat, and the flow field readjusts. Because lowering the surface brings the ice into warmer air, there is a feedback that accelerates melt once thinning has begun. This elevation feedback acts together with the albedo feedback and changes in atmospheric and oceanic circulation to determine the rate of ice loss through a deglaciation. The interaction between forcing timescales and ice sheet response timescales leads to characteristic patterns in the history of ice volume. When the period of the dominant forcing is comparable to the ice sheet response time, the system can exhibit a pronounced cyclic behavior in which ice sheets grow slowly over several tens of thousands of years and then retreat more rapidly. In the context of the early Pleistocene, the obliquity cycle of roughly 41,000 years provides a repeating pattern of high and low high latitude summer insolation. Conceptual ice sheet models forced by such a signal show that under appropriate parameter choices for snowfall melt and ice flow, ice volume can wax and wane with a main period similar to that of the obliquity forcing. In these simulations, ice sheets tend to grow over intervals of lower summer insolation as accumulation exceeds ablation, and then lose mass more rapidly during intervals of higher summer insolation when melt and calving increase. The asymmetry between slow growth and faster decay reflects the combined influence of ice dynamics elevation and albedo feedbacks, and the fact that a substantial fraction of the ice volume is located near the margins where climate warming can quickly produce negative mass balance. Spatial heterogeneity is important. Different sectors of a large ice sheet can experience different mass balance regimes at the same time because of variations in topography, proximity to moisture sources, exposure to warm or cold air masses, and contact with the ocean. For example, coastal sectors over shallow continental shelves may be more sensitive to changes in sea level and ocean temperature affecting the rate at which marine terminating outlet glaciers carve icebergs. Interior sectors resting on high plateaus may remain in positive mass balance, even as margins thin, providing a delayed source of ice that continues to feed outlet glaciers until the overall climate trend has progressed far into a warming phase. These spatial contrasts influence how total ice volume changes over time and can produce complex patterns in advance and retreat lines that are not captured by a single index of ice extent. Nevertheless, when viewed at the scale of the entire ice sheet, the mass balance integrates these regional differences into a net gain or loss that can be compared with the timing of orbital forcing. Feedbacks involving the solid Earth further complicate mass balance evolution. The weight of large ice sheets depresses the underlying lithosphere, displacing mantle material and causing the bedrock to subside. When ice thins or retreats, the bedrock slowly rebounds. This process, known as glacial isostatic adjustment, operates on timescales of thousands of years. As the bed subsides under a growing ice load, the surface elevation of the ice sheet does not increase as quickly as it would over a rigid bed, which can moderate the cooling effect of elevation gains. When the ice retreats and the bed rises, the ice surface can remain at relatively high elevations for some time, affecting local climate and mass balance. In regions where the bed lies below sea level, ostatic depression can increase the area of marine-based ice-making parts of the ice sheet, more sensitive to ocean conditions and to changes in global sea level. Over multiple glacial cycles, these interactions among ice thickness, bedrock elevation, and sea level influence the geometry and stability of ice sheets and the thresholds at which they advance or retreat. From a mass balance perspective, the combination of orbital forcing, atmospheric and oceanic responses, surface energy, balance ice dynamics, and solid Earth feedbacks defines a system in which continental ice sheets integrate small changes in high-latitude summer insolation into large variations in total ice volume over tens of thousands of years. The timing and magnitude of these variations depend on both the external forcing from obliquity precession and eccentricity, and on internal properties such as accumulation rates, flow laws, basal conditions, and the configuration of continents and ocean basins. In idealized models, when the external forcing is dominated by the 41,000-year obliquity cycle, and when internal timescales are comparable, the resulting ice volume history tends to show a strong component at the obliquity period, with individual glaciations growing and decaying in phase, with successive tilt minima and maxima, even though the full pattern can be more complex because of nonlinearity and feedbacks within the ice sheet system itself. Changes in continental ice volume are closely linked to changes in global sea level deformation of the solid Earth and the mechanical stability of ice sheets, especially where they extend onto continental shelves or rest on beds that lie below sea level. When large ice sheets grow on land water that was previously stored in the ocean, as liquid is transferred to the cryosphere as solid ice. This reduction in ocean water volume causes global mean sea level to fall. When ice sheets lose mass and shrink meltwater, and carved ice return to the ocean, raising sea level. Reconstructions of past glacial cycles indicate that global sea level can vary by many tens of meters between glacial maxima and interglacial periods. From the perspective of ice sheet dynamics, these variations in sea level modify the boundary conditions. At marine margins influence the extent of grounded ice on continental shelves and alter the stability of marine-based sectors that are partly supported by contact with the seabed. At the same time, the weight of a large ice sheet depresses the underlying lithosphere, and the solid Earth responds viscoelastically through glacial isostatic adjustment. As ice accumulates, the lithosphere bends downward, and the asthenosphere flows laterally away from the load, causing subsidence beneath the ice sheet and a slight uplift in peripheral regions. When ice thins or retreats, this pattern reverses. The lithosphere rebounds upward under the former ice center and subsides in the forebulge regions. The timescale of this adjustment is set by the viscosity structure of the mantle and typically spans thousands of years. Because the elevation of the bed relative to sea level affects where ice can ground, float, or retreat, glacial isostatic adjustment interacts with sea level changes to influence the geometry and stability of ice sheets over glacial cycle timescales. In marine-influenced regions, the combined effects of sea level change and bedrock deformation can cause grounding lines where ice transitions from resting on the bed to floating as an ice shelf to advance or retreat, even when local climate conditions remain similar. The gravitational field of a large ice sheet also modifies sea level. Ice sheet mass attracts ocean water, causing local sea surface height relative to the geoid to rise in the vicinity of the ice and to fall at greater distances. When an ice sheet grows nearby, sea level falls less than the global mean, or can even rise while far-field sea level falls more than the mean. When an ice sheet shrinks, the opposite pattern occurs. This spatially variable sea level response, together with isostatic adjustment, is often called sea level fingerprinting. For ice sheet stability, the relevant factor is the sea level at the ice margin and on the continental shelves adjacent to the grounded ice. In some regions, the gravitational and isostatic effects partly counteract or amplify the eustatic change produced by changing ocean volume, modifying the net pressure that ocean water exerts on ice fronts and the depth of water at grounding lines. Where ice sheets rest on beds that slope downward inland and lie below sea level, the configuration is described as a marine-based ice sheet on a retrograde bed. In these geometries, changes in grounding line position can lead to dynamic instabilities. The flux of ice across the grounding line depends on ice thickness, basal conditions, and the depth of water at the grounding line. If the bed deepens inland, a retreat of the grounding line into deeper water can increase ice thickness at the grounding line, which tends to increase outflow and promote further retreat. Conversely, an advance into shallower water can reduce thickness and outflow, favoring further advance. This marine ice sheet instability mechanism, derived from theoretical analysis and supported by numerical models, indicates that in some settings, the combination of bed topography and sea level change can allow small perturbations in climate or ocean forcing to trigger larger changes in the extent of grounded marine-based ice. Ice shelves, which are floating extensions of grounded ice sheets that occupy embayments and continental shelves, influence the stability of the grounded ice behind them through buttressing. Ice shelves transmit stresses from contact with sidewalls, pinning points, and the front of the shelf back into the grounded ice, resisting flow and reducing the rate at which ice is discharged across the grounding line. The strength of this buttressing depends on the geometry and thickness of the shelf, the presence of lateral contact, and the pattern of basal melting and surface accumulation. When basal melt under an ice shelf increases because of warmer ocean water, or when the ice shelf thins and breaks up because of surface meltwater, weakening buttressing is reduced and the grounded ice can accelerate. Over orbital timescales, variations in sea level and ocean temperature that accompany changes in global ice volume and climate can modify ice shelf thickness and extent, altering the balance between buttressing and outflow. These processes introduce additional pathways through which relatively small changes in high-latitude summer insolation transmitted through atmosphere and ocean can lead to larger changes in ice discharge and grounding line position. The bed material beneath ice sheets also affects their stability. In some regions, the bed consists of unconsolidated sediments, often described as regolith, or till which can deform under shear and provide a soft lubricated base. In other regions, the bed is composed of hard crystalline rock with limited sediment cover. The mechanical properties of these materials determine how readily ice can slide. A soft sedimentary bed tends to promote faster sliding and can allow the formation of fast-flowing ice streams that drain large volumes of ice from the interior to the margins. A hard bed with little sediment tends to resist sliding and favour slower deformation-dominated flow. Over successive glacial cycles, advancing and retreating ice sheets can erode and remove regolith, exposing more resistant bedrock and altering basal conditions. Although the details of these processes and their impact on long-term ice sheet dynamics are active research topics at the process level, it is well established that basal substrate water availability at the bed and bed roughness are key controls on sliding speed and therefore on the distribution of ice thickness and the location of fast-flowing outlets. Sea level bedrock elevation and bed properties interact with surface mass balance to determine where ice sheets are most stable and where they are vulnerable to retreat. For a given climatic regime, an ice sheet that rests on high continental interiors with beds well above sea level is generally more stable against marine influences than an ice sheet with large sectors grounded on low-lying or submarine beds. In the latter case, rising sea level during deglaciation can promote grounding line retreat, especially if ocean water at depth is relatively warm. Falling sea level during glacial growth can expose new continental shelf areas to grounded ice, allowing the ice sheet to expand horizontally, often onto beds with different topographic and sedimentary characteristics. Glacial isostatic adjustment modifies these relationships by changing the relative elevation of the bed and sea surface over time. The timescales of these solid Earth responses are similar to, or longer than, the timescales of ice thickness, changes driven by orbital forcing, so the system does not remain in static equilibrium, but instead evolves as ice-loading bedrock deformation and sea level change proceed together. Conceptual and numerical models that couple ice dynamics with sea level and solid Earth deformation show that these interactions can produce hysteresis in ice sheet extent, where the thresholds for growth and retreat differ, and where the memory of past loading influences present-day stability. In such models, an ice sheet may continue to exist under climatic conditions slightly warmer than those under which it initially formed because of the time lag in bedrock rebound and the configuration of the bed relative to sea level. Conversely, once retreat has progressed past certain grounding line positions on a retrograde slope, re-establishing a large ice sheet may require climatic conditions cooler than those that sustained it previously. From the perspective of glacial cycle dynamics, sea level bedrock adjustment and basal stability therefore act as moderating and amplifying elements that shape how ice sheets respond to obliquity, pace changes in high-latitude summer insolation, and to the associated atmospheric and oceanic responses. They do not generate the orbital forcing, but they influence how effectively that forcing is translated into gains and losses of ice volume, and into the specific geometries of ice sheet configurations at different stages of a glacial cycle. Geological and isotopic records provide the main empirical basis for reconstructing how global ice volume and deep ocean conditions vary over the timescales associated with orbital cycles. Because direct observations of ice sheet extent and climate exist only for recent centuries, information about earlier intervals in the Quaternary is obtained from natural archives that accumulate material over time, in the context of Ice Age pacing, deep sea sediment cores, and the oxygen isotope composition of microfossil shells preserved within them form a central line of evidence. Additional support comes from other marine and terrestrial proxies, but the global character and continuity of the deep ocean isotope record make it a primary tool for identifying dominant periodicities in ice volume. Marine sediment cores are obtained by lowering hollow tubes into the seafloor and extracting columns of sediment that have been deposited over hundreds of thousands to millions of years. In many parts of the ocean, sediments accumulate gradually as the remains of planktonic and benthic organisms, fine mineral particles and other materials settle through the water column and are buried. The resulting sequences contain layers that can be dated and analyzed for multiple properties, including grain size, chemical composition, and microfossil content. Among these, the ratio of oxygen 18 to oxygen 16 isotopes in the calcium carbonate shells of benthic foraminifera is widely used as an indicator of changes in global ice volume and deep ocean temperature. The basic principle is that during glacial periods, when large ice sheets store more water on land, the ocean becomes relatively enriched in the heavier oxygen isotope because lighter oxygen is preferentially transferred to ice. At the same time, lower deep ocean temperatures favour an increased incorporation of oxygen 18 into calcium carbonate during shell formation. As a result, higher oxygen 18 to oxygen 16 ratios in benthic foraminifera generally correspond to times with larger ice volume and colder deep waters, while lower ratios correspond to smaller ice volume and warmer deep waters. By measuring this isotope ratio down core and establishing an age model for the sediments, researchers construct time series of a quantity that closely tracks combined ice volume and deep ocean temperature over millions of years. In practice, multiple ocean drilling sites distributed across different basins are analysed and then combined into composite or stacked records that reduce local noise and highlight the global signal. One widely used example is a stacked benthic oxygen isotope record covering the last several million years that shows a series of glacial and interglacial cycles. When this type of record is examined for the interval corresponding to the early Pleistocene approximately from 2.5 million years ago to about 1 million years ago, the amplitude of glacial and interglacial oscillations is relatively modest compared with later times, and the spacing between successive peaks and troughs in oxygen isotope values is close to 41,000 years. Spectral analysis of such records, in which the time series is decomposed into its constituent frequencies, reveals a strong peak near the obliquity period of 41,000 years, with weaker power at precession-related periods and relatively minor contributions at the main eccentricity periods. This pattern is consistent with the situation in which, during the early Pleistocene, variations in global ice volume and deep ocean temperature inferred from the marine isotope record occur predominantly at the obliquity frequency. Establishing accurate age models for sediment cores is essential for interpreting these periodicities. Several methods are used. Biostratigraphy identifies the first and last occurrences or rapid abundance changes of particular microfossil species which can be correlated across sites. Magnetostratigraphy uses the record of geomagnetic polarity reversals preserved in the remnant magnetization of sediments to assign ages based on an independently dated reversal timescale. In some cases, radiometric dating of interbedded volcanic ashes or orthogenic minerals provides absolute age constraints. In addition, orbital tuning is applied, in which features of the sedimentary record, such as variations in oxygen isotopes, or sediment color that are linked to climate changes are aligned with calculated insolation or obliquity curves. When this approach is applied carefully, it refines age models and allows detailed comparisons between the timing of peaks in the marine isotope record and peaks in computed obliquity. For the early Pleistocene age models that combine magnetostratigraphy and orbital tuning consistently show that major transitions between relatively high and relatively low benthic oxygen isotope values occur near times when obliquity-driven high-latitude summer insolation anomalies pass through characteristic phases. This alignment does not specify the processes by which obliquity forcing is translated into ice volume changes, but it provides a quantitative description of the temporal correspondence between the astronomical obliquity cycle and the marine isotope record. Other types of marine proxies support this interpretation. Planktonic foraminifera from the upper water column also record oxygen isotope variations, which include a stronger imprint of local sea surface temperature. When records from multiple depths are compared, it is possible to separate to some extent temperature and ice volume components, and to evaluate how surface and deep ocean conditions co-vary on orbital timescales. In addition, changes in the relative abundance of microfossil assemblages, the content of ice-rafted debris and variations in carbonate preservation provide independent indicators of temperature ice margin position and deep ocean chemistry. Many of these records, when analysed over the early Pleistocene, show pronounced cyclicity at periods near 41,000 years, consistent with dominant obliquity pacing in the low-frequency band. On land, Loess and Paleosol sequences lake sediments and other continental archives record regional expressions of the same global climate variations. Thick deposits of wind-blown dust interlayered with soil horizons, for example, in parts of Asia and Europe show alternations between colder, drier conditions favourable to dust accumulation and warmer, wetter conditions favourable to soil formation. Age models for these sequences based on magnetostratigraphy and correlation with marine records indicate that many of the major transitions between Loess and Paleosol units during the early Pleistocene occur at intervals of roughly 41,000 years. Although these terrestrial records are influenced by regional factors such as monsoon strength and local vegetation, their pacing aligns with the obliquity-dominated cycles evident in the marine isotope stacks. Ice cores drilled through the Antarctic and Greenland ice sheets extend the direct record of climate and atmospheric composition back hundreds of thousands of years, with the longest reaching close to 800,000 years. These records do not cover the full early Pleistocene interval, but provide high-resolution information for later glacial cycles. Within their temporal range variations in oxygen, isotope ratios of ice-trapped gas composition, and other properties document repeated glacial and interglacial fluctuations in temperature and greenhouse gas concentrations. Spectral analysis of these shorter records reveals power at obliquity precession and eccentricity-related periods, with the relative importance of each varying between intervals. When overlapped with the marine isotope record, the ice cores confirm that periods of higher global ice volume inferred from ocean sediments correspond to colder conditions and lower greenhouse gas concentrations in polar regions. For the identification of the early Pleistocene 41,000-year pacing, the main contribution of ice cores is to provide constraints on more recent glacial cycles and to support the interpretation of oxygen isotope variations as indicators of ice volume and temperature changes. Taken together, deep-sea sediment cores, marine isotope stacks, continental archives and ice cores form a coherent set of geological and isotopic records. For the early Pleistocene interval, their combined evidence shows that global ice volume variations and associated climate changes are organized primarily around a 41,000-year rhythm that matches the obliquity cycle derived from astronomical calculations, while other orbital frequencies are present but less dominant in the low-frequency part of the spectrum. In long marine isotope records that span both the early and the late Pleistocene, a marked change appears in the dominant pacing and amplitude of glacial cycles between about 1,200,000 and about 700,000 years ago. This interval is commonly referred to as the mid-Pleistocene transition. Prior to this transition, as described earlier, the stacked benthic oxygen isotope record is characterized by relatively modest glacial-interglacial contrasts and a spectral peak concentrated near the 41,000-year obliquity period. After the transition, the isotope record shows larger amplitude variations, with deeper glacial maxima and higher interglacial minima, and the spacing between major terminations increases toward values closer to 100,000 years, although the pattern is not strictly periodic. Spectral analyses of long composite records highlight this shift. For the interval older than roughly 1,200,000 years, power in the low-frequency band is dominated by the obliquity peak, with subordinate contributions at precession-related frequencies and limited power near the main eccentricity periods. For the younger interval covering the last 700,000 to 800,000 years, power at periods near 100,000 years becomes comparable to or exceeds that at 41,000 years, while the obliquity and precession peaks remain present, but contribute differently to the overall variance. The transition between these two regimes does not occur as a single sharp boundary, but unfolds over several 100,000 years, during which both 41,000-year and longer cycles appear in the record. Detailed inspection of individual glacial cycles across the mid-Pleistocene transition shows that in the earlier part of the Pleistocene, oxygen isotope oscillations are more nearly sinusoidal and symmetric, with relatively gradual transitions between higher and lower values that align well with successive obliquity minima and maxima. In the later Pleistocene, cycles are more asymmetric. Ice volume tends to increase over extended intervals, with benthic oxygen isotope values drifting toward heavier compositions over 60,000 to 90,000 years, followed by relatively rapid transitions toward lighter values over several thousand to perhaps 10,000 years that correspond to major deglaciations or terminations. These terminations are spaced at intervals that cluster around 100,000 years, though there are variations and occasional skipped or merged cycles. The long-term trend across the mid-Pleistocene transition also includes a gradual deepening of glacial maxima, suggesting that successive glaciations in the later Pleistocene achieve greater global ice volumes than those characteristic of the early Pleistocene 41,000-year regime. Age models for marine isotope stacks indicate that the onset of larger amplitude, longer space cycles is gradual. Some records show episodes of increased cycle length and amplitude beginning as early as 1,400,000 years ago, with a more complete shift to predominantly longer cycles after about 900,000 years ago. Different stacks and individual core records show some differences in the precise timing and structure of the transition, reflecting local depositional conditions, age model uncertainties, and the influence of regional oceanographic changes. However, the overall pattern of a shift from obliquity-dominated relatively low amplitude cycles to a regime with stronger 100,000-year variability and larger ice volume changes is robust across multiple datasets. In addition to benthic oxygen isotopes, other proxies track aspects of the mid-Pleistocene transition. Records of ice-rafted debris in North Atlantic sediments show evidence for more extensive and frequent delivery of icebergs to lower latitudes in the later Pleistocene, consistent with the presence of larger ice sheets that extend farther onto continental shelves and into ocean basins. Changes in the composition of foraminiferal assemblages, carbonate preservation, and trace metal ratios in deep-sea sediments indicate modifications in deep ocean temperature ventilation and carbon storage that accompany the growth of larger glacial ice sheets. Loose and paleosol sequences on land show thicker and more strongly expressed alternations between dust-dominated and soil-dominated units in the younger Pleistocene, suggesting stronger or more persistent contrasts between glacial and interglacial climates. Together, these records imply that not only the periodicity, but also the amplitude and spatial expression of glacial cycles change across the mid-Pleistocene transition. The relationship between the timing of isotope peaks and the phases of orbital elements evolves as well. In the early Pleistocene, many studies report that maxima and minima in benthic oxygen isotope records are closely aligned with obliquity extrema, supporting an interpretation in which obliquity paste insolation variations at high latitudes provide the primary external timing for glacial cycles. In the later Pleistocene, the alignment becomes more complex. Terminations often occur near times of strong high-latitude summer insolation anomalies that reflect combined contributions from obliquity and precession, and there is an apparent clustering of major deglaciations near times of larger eccentricity when precession-related insolation variations are more pronounced. The 100,000-year pacing evident in the isotope record is broadly similar to the main eccentricity periods, but the eccentricity variations themselves are small in terms of their direct effect on annual mean insolation. This mismatch between the magnitude of eccentricity-related insolation changes and the magnitude of ice volume changes inferred from the isotope record is a central observation in studies of quaternary climate dynamics. From the standpoint of the data alone, the mid-Pleistocene transition marks a change from a climate system in which global ice volume responds in a way that is strongly organized by the 41,000-year obliquity cycle, to a climate system in which ice volume variations exhibit a larger component at periods near 100,000 years, with more pronounced asymmetry between growth and decay phases and with deeper glacial states. The transition occurs, gradually involves overlapping frequencies, and is recorded consistently in multiple marine and terrestrial archives, establishing it as a robust feature of quaternary climate history that any explanation of orbital scale ice age pacing must take into account. Explanations for why many early Pleistocene glacial cycles follow a 41,000-year rhythm, while later cycles lengthen toward intervals near 100,000 years, focus on how the climate system, and especially large ice sheets and greenhouse gases, respond to orbital forcing that is itself well understood. In a simple linear system that responds proportionally and without thresholds, the climate response would be expected to show peaks mainly at the frequencies present in the insolation forcing dominated at high latitudes by obliquity and precession. The strong emergence of 100,000-year scale variability in the later Pleistocene, despite the relatively small direct insolation changes associated with eccentricity, indicates that non-linear processes, thresholds, and internal feedbacks play a significant role. One group of mechanisms emphasizes ice sheet dynamics and the way in which large ice masses integrate and filter the orbital forcing. Ice sheets evolve over timescales comparable to or longer than the 41,000-year obliquity cycle. Their growth and decay are limited by thresholds in mass balance, basal sliding, and marine stability that can cause the system to skip some obliquity cycles and to produce larger, more asymmetric variations in ice volume. In conceptual models, ice volume is allowed to increase gradually when high-latitude summer insolation is below a certain threshold, with accumulation exceeding ablation and to decrease more rapidly when insolation rises above a higher threshold that represents conditions under which large-scale melting and marine retreat occur. When such models are forced with realistic obliquity and precession-driven summer insolation, they can generate sequences of glacial cycles in which several obliquity minima contribute to the slow buildup of ice. But deglaciation occurs only when a strong combination of high obliquity and favorable precession phase produces unusually intense high-latitude summer insolation. This behavior can produce cycles with average spacing closer to 100,000 years, and a sawtooth shape characterized by slow growth and rapid termination, similar to the later Pleistocene isotope records. In these models, eccentricity does not act primarily through its small direct effect on insolation, but by modulating the amplitude of precession-driven changes in seasonal insolation. When eccentricity is higher, some precession cycles produce particularly strong peaks in summer insolation that are more likely to exceed the deglaciation threshold. When eccentricity is lower, precession-related peaks are weaker, and even high obliquity may not trigger a termination. In this view, the 100,000-year band in the climate record arises from the combination of an obliquity-dominated baseline forcing amplitude modulation by eccentricity and thresholded ice sheet response. A second line of explanation involves the mechanical properties of ice sheet beds and their evolution over successive glacial cycles. One hypothesis proposes that during the early Pleistocene Northern Hemisphere, ice sheets frequently advanced over extensive layers of unconsolidated sediment or regolith, which facilitated sliding and limited ice thickness and stability. Under these conditions, ice sheets may have been more responsive to the 41,000-year obliquity cycle, growing and shrinking in step with changes in high-latitude summer insolation. Over time, repeated glaciations could have eroded regolith and exposed more resistant bedrock. As beds became harder and rougher, ice sheets could grow thicker and more stable for a given climate, altering their response timescale and increasing the importance of internal dynamics and thresholds. Numerical ice sheet models that include a transition from soft to hard beds can exhibit a shift from smaller obliquity-paced cycles to larger, longer cycles with more pronounced hysteresis. While geological evidence supports significant erosion and regolith removal in some formerly glaciated regions, the extent to which this process alone can account for the mid-Pleistocene transition remains an active area of research, with ongoing work comparing model predictions and sedimentary records. A third group of mechanisms focuses on greenhouse gas concentrations, particularly carbon dioxide, and their feedbacks with ice sheets and the ocean. Atmospheric carbon dioxide affects global climate through the greenhouse effect, and on orbital timescales, its concentration is influenced by exchanges with the ocean and the terrestrial biosphere. Proxy records indicate that glacial periods are associated with lower atmospheric carbon dioxide, while interglacials have higher concentrations. Changes in ocean circulation, biological productivity, and carbonate chemistry can alter how much carbon is stored in the deep ocean versus the atmosphere. Some modeling studies suggest that a gradual long-term decline in baseline atmospheric carbon dioxide over the Pleistocene, possibly related to tectonic and weathering processes, could have made climate more favorable to larger ice sheets and stronger glaciations. In such scenarios, the same orbital forcing would produce different ice volume responses as background carbon dioxide decreases, potentially allowing a transition from smaller, more linear 41,000-year cycles to larger, more nonlinear cycles with longer effective periods. Other studies emphasize that state-dependent carbon cycle feedbacks in which ocean stratification, nutrient supply, and sea ice conditions control the efficiency of carbon storage in the deep ocean can amplify ice sheet-driven climate changes and contribute to the pacing of terminations. However, proxies for carbon dioxide and ocean conditions across the mid-Pleistocene transition still have uncertainties, and no single carbon cycle mechanism has been conclusively identified as the primary cause of the shift in periodicity. Additional mechanisms involve interactions among ice sheets, sea level, and solid Earth deformation. As ice sheets grow and shrink, they depress and release the lithosphere, and change global sea level, influencing the geometry and stability of marine-based sectors that rest on beds below sea level. Isostatic adjustment and sea level change can alter grounding line positions and the susceptibility of ice sheets to marine ice sheet instability. Over successive glacial cycles, these processes can modify which parts of the continental shelves become ice-covered, and how ice streams and ice shelves are configured. Some modelling work indicates that such interactions can contribute to longer, more asymmetric glacial cycles by changing the effective thresholds for growth and retreat as the solid Earth and sea level respond to cumulative ice loading. Yet isolating this effect in geological records is challenging, and it likely operates in combination with other feedbacks. Across all these proposed mechanisms, there is broad agreement on several points. The orbital forcing itself, including the 41,000-year obliquity cycle precession and eccentricity modulation, is well quantified by astronomical calculations and does not change in a way that can by itself explain the mid-Pleistocene transition. The early Pleistocene marine isotope record shows a dominant obliquity frequency consistent with a climate system in which ice volume responds relatively directly to obliquity-paced high-latitude summer insolation. The later Pleistocene record exhibits larger amplitude, more asymmetric cycles with a strong 100,000-year component, indicating that internal processes within the climate ice sheet carbon cycle system modify the response to the same basic orbital forcing. There is also agreement that ice sheet dynamics, including thresholds nonlinearity, and feedbacks involving albedo elevation and basal conditions, are central to this modification, and that greenhouse gas and ocean circulation feedbacks contribute additional amplification and structure. What remains uncertain and is the subject of ongoing research is the relative importance of each proposed mechanism, the timing and magnitude of any long-term changes in boundary conditions, such as regolith extent and baseline carbon dioxide, and the degree to which different processes interact to produce the observed shift from 41,000-year dominated cycles to a regime with prominent 100,000-year variability. Different modelling frameworks ranging from simple conceptual models to more comprehensive coupled climate and ice sheet models can reproduce aspects of the data under different parameter choices, but no single model or mechanism has yet achieved universal acceptance as a complete explanation. As a result, the current understanding can be summarized as follows. At the process level, the obliquity cycle provides a persistent, well-defined external pacing of high-latitude summer insolation. Ice sheets, oceans, atmosphere, and the carbon cycle respond through a network of feedbacks and thresholds that can reorganize the spectral distribution of climate variability. And the emergence of longer, larger amplitude cycles in the later Pleistocene reflects changes in this internal network rather than changes in the underlying orbital forcing, with the exact pathways linking 41,000-year tilt variations to 100,000-year scale ice age cycles remaining an active topic of investigation